Hello, everybody, and welcome to your Historical Geology Midterm Review. And we're going to be going through this whole study guide that you should have found online, and you can see that it's quite large, so I'm not going to waste any time about getting right into the material, okay? So I'm just going to start here. Hopefully by now you should know all the details about the test, and I'm going to step right on into the material, okay? So the first thing that we studied in this class is philosophy of science. So you should be able to understand, the main thing I wanted to get across to you with philosophy of science is you should be able to understand where science starts and where it ends. So what kind of subjects are valid subjects of scientific inquiry and which are not. That's the main thing I wanted to communicate to you with this lecture. So you should be able to understand and mention all the criteria necessary for a question to be answerable by science. Okay. Now you might ask, well, what on earth are you talking about? So the things that we talked about are, first of all, that science studies only things that are physical or natural. Okay, and those are just kind of synonyms in this case, but it only studies things that occur in the physical natural universe, things that are connected to mass, energy, time, space, things like that. Okay, so we're not interested in thoughts and ideas and emotions, the mind and things like that. Okay, we're more interested in atoms, energy, matter, things that exist in space. So if that, hopefully that makes sense to you. Another thing that we talked about is things need to be falsifiable. So, whoops, I forgot my L. Falsifiable. Now, what does falsifiable mean? Falsifiable means that it has to be capable of proving true or false by evidence. Okay, and that's an important part right here. If you just put on the test capable of being proven true or false, that's not correct, because lots of things are capable of being proven true or false. For example, mathematical truths are capable of being proven true or false, but we don't prove them true or false by evidence. So an important part of this is by evidence, and evidence are things that make it evident, things that again that are observed. Okay. Another thing you could put here instead of by evidence is by observation. Okay. So that's another thing you can put. And remember that science is always tied to observation. We often refer to science as being empirical, and that means based on observation. Okay, so that's another thing. Falsifiability. A third thing here that you should know is reproducibility. So reproducibility is the idea that a scientist or whoever should be able to come and reproduce your observation and your results. So there are certain things. So for example, in the lecture, I give the example of historical events. You know, single historical events are often not reproducible. So we don't study those usually with science, right? We have a whole other subject called history, which we study those things with. So you have to be able to go and reproduce whatever results. So that's another aspect of science, and hopefully that'll make sense to you. If you want more details, you can go back to the lecture. So another question that I ask on the test is about hypotheses versus predictions versus theories. So let me kind of delineate what all these different things are. So first of all, we can start with a hypothesis. So hypothesis is something that seeks to explain. So it always is trying to explain something about nature. So it's a kind of an explanation, and it's often causal. Causal means that it's saying, you know, X happens because of Y, right? So we're trying to explain the why something happens. Okay, hypotheses always explain why. Okay, so you should kind of connect that question why to a hypothesis. So we're trying to explain why something happened. We're trying to explain the causes and explain. And by the way, one thing we have to show here is a hypothesis is just, maybe you could say, a guess in a way, because it doesn't have a lot of evidence. Okay, doesn't have a lot of evidence yet, or experiments or results that back it up yet. Okay, so that's a hypothesis. Now, a theory is different. A theory is something that actually has some evidence or experiments that are backing it up now. Okay, So there's some experimental results. Maybe if somebody did an experiment to back up their hypothesis and it was successful, then we can maybe elevate that to a theory. Okay. Another thing that often gets confused here that I wanted to talk about is a prediction. So prediction, sorry, I'm kind of erasing some of this stuff so I have more room to write. A prediction. So what's a prediction? A prediction is simply an expected outcome. What you expect to see when you do an experiment or whatever you're doing with some expected observation. So a lot of people get those hypotheses and predictions confused for some reason, and I'm not exactly sure why, because they're totally different things. But if you predict to see, for example, I gave, in the lecture I give the example of the trees. We ask, why do they lose their leaves in the winter? So a hypothesis that would explain why that is would go like, well, they lose their leaves in the winter maybe because it gets cold. And a prediction would be, if that's true, then maybe very cold areas should, all the trees should lose their leaves, whereas very warm areas, they shouldn't lose their leaves, or something to that effect. Okay. So prediction is just an expected outcome. Okay. Now, moving on to the metric system. So I think those are the only real questions I ask about, philosophy of science. Okay. So I think if you know the answer to those two things, you should be good. Another thing that we talk a lot about is the metric system. So I don't think you need to know all 7 independent dimensions of measurement and their metric system bases, but you should definitely know the ones for mass, time, distance, and temperature. Okay, those things are subjects that we talk about in this class. So mass is kilograms, that's the base unit. Time is a second. Distance is a meter, not a kilometer, but a meter. And temperature is either Celsius or Kelvin. Okay, and I would accept either on the test. Now, I would just want you to think about maybe some distractor answers I could put on the multiple choice for these. So if you think about that, something I might put for mass, things that are not metric system base units are pounds, right? Pounds, that's an English system unit. Or maybe another thing I could put on there or not grams, but maybe ounces or something like that. So that would be a distractor. Think about that also for distance. I could put on there miles, or perhaps I could put inches or something, and that would be a distractor. So those are not true, right? So you don't want to put those on your test. So those are distractors. But I'm just trying to get you to think about that, okay? So anyway, moving on, you should also know some of the basic metric system prefixes, how to convert between metric system units. Okay, so remember that when you convert between metric system units, it's always just a matter of moving the decimal. So maybe you're moving the decimal like this or whatever. That would be 3 jumps, and or maybe you're moving it to the left. Okay, whatever it is. But you're usually just making the decimal point move, and that's all you're doing with metric system conversions. Okay, when you go metric to metric. Now it's different when you go English to metric. So we could give you some examples. Let's see, I don't think I have any examples down below, but you should know how to do something, for example, like how many meters in, or how about this? How about we say how many centimeters in a, how about a kilometer? And I think I give that one actually in the lecture. But so let's say that we start off with 1 kilometer. Okay, 1.0 kilometers. I'm going to put kilometers up there kind of small so that I have room to move my decimal point. Now you might remember that the way that the prefixes go, we have at the top mega. That's 10 to the 6. And then we go after that kilo. It skips down 3 to 10 to the 3. And then we have a hecta. That's 10 to the 2. And then a deci. A deca. That's 10 to the 1. And then we have a base unit. That's our base unit, whatever it is. That's 10 to the 0. And by the way, 10 to the 0 just equals 1, in case you forgot about that with exponents and algebra and all that stuff. So then after that, we start to make the base unit smaller. So instead of scaling it up bigger, we're making it smaller. So after that, we go to a deci. That's 10. It's actually 1 over 10, so which is about 0.1. Then we go to centa. That's 1 over 100. And then we go to mille. That's 1 over 1,000. And then finally, the only thing you should know for this test, it goes, of course, beyond mega and micro, but I'm not going to make you know that, but that's 10 to the negative 6. Okay. Or sorry, 10 to the 6. 1 over 10 to the 6. Get myself all confused. 1 over 10 to the 6. Okay. So if you take a look at this, and we saw how many centimeters in a kilometer. So we have the base unit. That's a meter. Kilometers up here, and you'll notice that we'll have to go 1, 2, 3 to the base unit. Don't forget the base unit. 4, 5 to get the centimeter. Okay. Another way that you could do it is subtract the exponents. So notice we're 10 to the 3 up here, and we're 1 over 100 here, which is 10 to the negative 2 here. The difference between an exponent of 3 and an exponent of negative 2 is 5. So because 3 minus a negative 2 is equal 5. Okay, so that tells you how many jumps you have to do. So I'm going to start off with 1 kilometer. I'm going to go 1, 2, 3, 4, 5 jumps. I'm going to put the decimal point there, and then I have to fill in zeros like that. Okay, and you'll notice if I write this all now, it's 100,000. Okay, so that's what you would have to do on the test. And guess what? That would be multiple choice, so you wouldn't have to figure that out necessarily on your own, but you would have to be able to pick it out of a crowd of different possible answers, right? Now, you might have to do, if I even have this on the test, I only maybe have one question about it. But I want to talk about English system to metric system conversions. So the way that this would work is it would be multiple choice, and you don't have to, I don't allow you to have calculators on the test. So you can't do these like really in-depth calculations. So don't worry about that. But I do want you to know kind of ballpark. So this is what I mean by that. You might have a question on there that's like, how many, for example, how many miles, it's an English system, right? Miles is English system, in 16 kilometers. Okay, so it just so happens that there's 1.6 kilometers per mile. So the answer to this would be 10 miles. Okay, so there'd be 10 miles in 16 kilometers. So maybe one of your possible answers would be 10 miles. Another one might be 160 miles. Or another one might be, 0.1 miles. Or something might be, 1,600 miles. So I'm just kind of trying to show you that you just need to sort of have a basic like ballpark understanding of how these units convert. So hopefully you would be able to recognize, okay, it's 10 miles, right? Because there's about 1.6 kilometers per mile. So anyway, it would be good for you to just memorize pretty close to how each of these units converts. So I'm just gonna write this out for you. So for inches to centimeters, you have 2.54 centimeters per inch. Okay, so that means that a centimeter is smaller than an inch. Okay, for meters and feet, you have 3.28 meters per foot. For kilograms to pounds, you have 2.2 pounds per kilogram. For miles and kilometers, you have, like I said, 1.6 kilometers per mile. Okay, so you should just know, like I said, ballpark estimate of how many miles there are in a kilometer, how many pounds in a like I could give you a question, how many kilograms are there in 10 pounds or something? Well, you'd have to divide that by 2.2, and you're not going to have, it's not going to be like, oh, is it 4.5 or is it 4.54 or is it 4.53? It's not going to be that precise. It's just going to be a ballpark. So hopefully that makes sense, what I'm trying to say to you. So I'm going to, just in the interest of time, I'm going to move on here. So global geography, what's the special name given to the 0 degree meridian? That is, hopefully you know by now, that's the prime meridian. Okay, just be very careful, because you know that if you have Earth, you have the poles here, North Pole, South Pole, right? That meridians are the ones that go pole to pole like that, right? So those are your meridians. The prime meridian is the one that happens to go through Greenwich, right? Now, the other things are the lines of latitude, right? Those are called parallels, and they go like that. And remember that they don't touch each other, okay? So do meridians intersect? Yes, they do. They intersect at the poles. Do parallels intersect? No, they don't. They're parallel, and that's what parallel means. It means they don't intersect, right? Which parallel is furthest from the poles? Well, you'll notice that here's the pole up here. Here's the pole up here. The one that's furthest from the pole is the one that's smack dab in the middle, and that's the equator, right? So it's the equator. Now, I'm not going to ask that question. You should know what the climate is like, how climate changes according to latitude, because that comes up a lot in this class. So 75 degrees south, that would be very far south. So anything that's greater than 66.5 degrees, north or south, is going to be cold, okay? And that's a polar climate. And anything that is between 23.5 north to south, okay, so it's anywhere in between 23.5 degrees, or I should say, maybe I should just say less than 23.5 degrees north or south, that's going to be hot. It's a tropical climate, okay? Now, the tilt of the rotational axis relative to the ecliptic plane. So if you have the sun, the planets actually all rotate in a plane, in a flat plane. Okay, so here's Earth. Okay, I know that I've made Earth bigger than the sun, but that's okay. Now, the tilt, this would be a 90-degree perpendicular, right? So that would be perpendicular to the plane. And the tilt of our rotational axis is about 23.5 degrees away from the perpendicular. And you'll notice that's the same as the tropical lines, okay? The Tropic of Capricorn and Tropic of Cancer, okay? So the answer is 23.5 degrees. All right, now the way that you're going to get this on the test is you're going to have a map. Possibly you're going to have a map like this. By the way, one thing I wanted to explain is that the way your test works is that you have a bank of maybe 80 questions. And I think that I have all the questions here. You know, that's what we're doing right now is we're looking at all these questions, right? And I don't know how many we have here. There's a lot. We'll get through these all in good time. But you have 70 questions. So I think like all of these are on there, and you're going to get like a random choice, I think, of like maybe 60 questions or something. So I just want to let you know that not everything that we look is going to be on your particular test, but it's all going to be scrambled up, and people are going to get the questions in different order, and they're going to get some different questions. So just be aware of that. That's how the test works. So it's going to pick randomly out of a bank of like 70 to 80 questions. Okay, so the way that this question is set up on the test is you're going to have a map like this, and it's going to have things like A, B, C, D, or something like that. And then it's going to say, like, where are the Andes Mountains? Okay, well, the Andes Mountains would be A. Where are the Rocky Mountains? Okay, the Rocky Mountains would be B. Where's Lake Baikal? Lake Baikal would be C. Okay, where are the Philippine Islands? Saying that'd be D, right? So that's just gonna kind of how that's gonna be set up. Okay, so I'm not gonna do everything that's on here. I gave you a bunch of features. You should know where they are, and if you don't know where they are, get a map and look them up. I'm not gonna give you all these. Well, I guess I could give you all these pretty easily. So here's Hudson Bay. There's Hudson Bay right there, and the Aleutian Islands are right here. The Japanese islands are right there. There's the Philippines. There's Sumatra. Okay, Lake Baikal, like I said, is right there. The Andes are right there. The Appalachians are right here. Okay, I can't remember if there's anything else on there. Oh, Greenland is right here. Iceland is right there. Okay, so I think did I get everything on there? Himalayas are just between right at kind of the northern edge of India, right there. Okay, Let's see, did I get everything there? I think so. Gulf of Mexico. I hope you know where the Gulf of Mexico is, since we live near the Gulf of Mexico. So anyway, going on to basic Earth structure. This is a very important lecture that we had, and a lot of questions from that lecture are going to be on the test. Okay, so just be aware that probably all of these are on the test. So you should be very well prepared for this stuff. Okay, so how old is the Earth? You know that's going to be on the test because it's historical geology. So according to radiometric dating, it's 4.5 billion years. Okay, and the way that question is worded, it'll say, according to scientists, according to radiometric dating, how old is the Earth? So you would put 4.5 billion years. That's how old scientists think it is according to radiometric dates. Okay, so what are the 4 basic layers or spheres of the Earth? So remember how Earth works. Okay, you have the crust. That's the outermost layer. It's very small. Then you have the mantle. Mantle is very large. Mantle is actually about 2/3 of the mass of Earth, so it's the biggest layer. Then you have the outer core, and then finally on the inside you have the inner core. Okay. Remember that the outer core is the only one of those layers that is actually a molten. Okay, so that's the answer here to number 17 is the outer core. Okay, 4 most abundant elements in the whole Earth. You should know that. So that is starting with iron, silicon, oxygen, and magnesium. Okay. Now in the crust, it's a little bit different. Okay, and remember, be very careful when you're answering these questions. Make sure. Am I talking about the crust or am I talking about the mantle? Okay, because or talking about the whole Earth or am I talking about the crust? So be very careful. Make sure you read the question carefully. So the answer to that is silicon, oxygen, iron, and aluminum. Okay, so it's really the same as this, except we've swapped out magnesium for aluminum. Okay. What's the composition of the core? It's iron. It's iron-nickel alloy, plus some lighter elements. But if you know it's iron, that's the main thing. Iron is probably 90% of what's in there. What proportion of Earth's mass is in the mantle? That's 2/3. In the crust, it's actually less than 1%. Okay, and then in the core, it's 1/3. What is the dominant rock type on the ocean floor? The dominant rock type is basalt. Okay. Now, what are some differences? This is a very important question. I ask, on your test. Whoops. How'd that happen? I got way down here. That's weird. Okay, on your test. Whoops, I'm still not here. On your test, you're going to have a lot of multiple choice and true, false, and other kinds of questions that are kind of, you select the answer from a list. But you're also going to have some questions where you have to write. And you'll maybe have 4 or 5 questions that are like that, where you have to write. So with that being said, this is one that I put on there that you need to write about. So you should know the difference between continental crust and ocean crust. And I think on the test I have you mention at least 4 differences. So, and by the way, you need to explain this like in a paragraph. I don't really take bullet points for full credit. Okay, a lot of people do end up putting bullet points, but they don't usually give them full credit. So I want you to write a nice, paragraph that explains the differences here with some nice details about it. So first of all, ocean crust is denser, okay? So ocean crust is about 3.0 grams per cc in density, whereas continental crust is less dense, about 2.7 grams per cc. The average thickness of ocean crust is 5 kilometers, whereas continental crust is much less. It's about, much more. It's about 30 kilometers. So continental crust is thicker, can be up to 70 kilometers. Ocean crust is typically 5 to 7 kilometers, so it could be quite thin. Average age. The ocean crust is younger, much younger. Much younger. And for historical geology, you should definitely know that. Okay, it's much younger. Maybe only has an average age of maybe 80 million years or something like that, maybe 100 million years. Whereas the average age of the continental crust is very old, about 2.5 billion. And of course, we get rocks that are up to 4 billion years old, according to radiometric dates on the continental crust. Okay. Now, the average rock type here on the ocean crust, it is basalt. And here on the continental crust, it is diorite, which is an intermediate igneous rock. Okay, composition. Whenever I ask for composition, I'm asking for mafic, intermediate, or felsic, or ultramafic. So you should give one of those compositional terms. So composition of the ocean crust is mafic. Basalt is a mafic rock. Diorite is an intermediate rock. Okay, the average elevation. So the average elevation here is -4 kilometers. And over here, it is about 500 meters. Okay, so this one's pretty obvious, but obviously, continental crust sits higher, has an average higher elevation than the ocean crust, right? So that's why we're not underwater right now. Okay, so what's the primary difference between mantle asthenosphere and mantle lithosphere? So asthenosphere and lithosphere. Remember, if we take a look at the Earth, I'm going to kind of draw. Well, actually, I shouldn't draw it so much like that. I should maybe just draw kind of the upper 100 kilometers or so. And you might remember I had you do this on the test. Or not on the test, on the lecture assignment. Sorry, pardon me. So we have... Oops. Why isn't that working? Oh, there it goes. So, we have the crust, right? There it goes. So we have the crust... And then we have the continental crust there. That's like ocean crust. This is continental crust. And then below that we have the mantle. And then there's actually kind of a line that delineates mantle asthenosphere and mantle lithosphere. Okay, so I'm going to put here mantle lithosphere and mantle asthenosphere. So the difference between these is that mantle is mantle, and it's the same in terms of composition. But mantle lithosphere is mechanically different. It behaves differently. It behaves more like a stone. So I can maybe put here stone-like. So it kind of behaves more like what you're used to when you think of a stone. It's hard, it's brittle, it fractures and cracks and breaks into pieces. Mantle asthenosphere is different. It would act weird. If you had a bunch of mantle asthenosphere in your hand, well, your hands would disintegrate and fire. But if you could play with it, it'd be kind of mushier, I would say. And it would be kind of more like soft butter or silly putty, something like that. So it can actually convect, it can move, can form, deform, fold, and so it's a little bit more like malleable. We actually the word that we use for that is plastic. It's more plastic. Okay, so that's mantle asthenosphere and mantle lithosphere. It's a mechanical difference between the two. Okay, so moving along, minerals. You should know the criteria for minerals. There are 5. So those are natural. It has to be naturally occurring. It has to be solid. It has to have a crystal structure. So I put extal means crystal. Okay. It also needs to have a chemical formula. And it also, number 5, needs to form by some kind of geologic process. Okay, so biologic processes, usually we don't count things like that. All right, so you need to be familiar with some of the more common minerals of the crust. You might need to know some mineral formulas for easy ones like quartz. Quartz is SiO2. You should know that feldspar is the most common mineral of the crust. Olivine is the most common mineral in the mantle. The mineral formula for olivine, you should probably know that. It is Fe or Mg. You could have either one. 2, that means there's 2 of those, SiO4. Remember that SiO4 is just one of those silicate molecules. Speaking of that, you should know that a silicate molecule looks like that with a silicon in the middle and 4 oxygens at each corner. Okay, there's one back there that you can't necessarily see. The silicate minerals are quartz, feldspar, olivine, pyrite is not one, pyroxene, amphibole, mica. Calcite is a non-silicate. It is actually calcium carbonate, so it's a carbonate mineral instead of a silicate mineral. Notice how the mineral formula for olivine, it's a silicate and it contains silicon, right? Quartz contains silicon as well. That's what makes it a silicate. So notice that calcite does not have that, so it's a carbonate mineral. So it's a non-silicate, okay? You should know that non-silicates are softer, typically, and more erodible. So they're softer and easier to erode and destroy. Okay, so calcium carbonate is primary among those. All right, so I think that's enough to know maybe about minerals. Just some of these mineral formulas I already mentioned above. Calcium carbonate is calcite. Hematite is Fe2O3, so it's an iron oxide. Quartz is SiO2. Feldspar is either sodium or potassium, so you put that in parentheses, sodium or potassium. AlSi3O8. And olivine, like I said, is either iron or magnesium 2. It means there's 2 of them, SiO4. Okay, so you should know those mineral formulas. You should also know some of the most common minerals of the crust and mantle. So for the crust, know that it's feldspar. That's the most common mineral. And for the mantle, know that it's olivine. And the difference between a silicate mineral and a non-silicate. So like I said, silicate minerals have silica, right? That's all that is to it. You should also be able to list maybe an economic use of some minerals. So I talked a lot about those in the lecture. I'm not going to list them all out right now at this moment, but you should just kind of generally be familiar, because I think on the test I might ask you for, like, can you name one economic use of one mineral, something like that. So you should be able to answer a question like that. So for igneous rocks, you should know that, first of all, you should know the 3 major rock types, right? So that's igneous, sedimentary, and metamorphic. Okay. And you should know the different compositional features that we talk about, or compositional types that we talk about. So the ones we talk about are felsic, and there's intermediate, which is in the middle. I don't really need to talk about that because it's just intermediate between mafic and felsic. And there's mafic. Now, mafic is low in silica, and it's high in iron and magnesium, like that. Whereas felsic is high in silicon, sodium, potassium, and aluminum. Okay, those are the things that are different chemically between felsic and mafic. Intermediate, it's just that. It's intermediate between the two. It has intermediate levels of sodium and potassium and aluminum, and intermediate levels of iron and magnesium, and intermediate levels of silicon. So, that's easy. Now, the difference between plutonic rocks and extrusive rocks. Remember that plutonics are ones that form below surface. So Pluto, remember, is god of the underworld. So those are below the surface. So they harden from a magma, but they never actually make it to the surface. Like a volcanic rock, right? Volcanoes, actually erupt on the surface and the lava comes out, and it's more of a surface phenomenon. Okay, so that's the difference between extrusive volcanic rocks, plutonic intrusive rocks. And just realize that plutonic intrusive means the same thing. Volcanic extrusive means the same thing. Okay. Now, for these following igneous rocks, you should know whether they're mafic, intermediate, or felsic. We're going to talk about these down here, so I'm going to skip over. For the different textures, you don't really need to know glassy, porphyritic. I'm kind of trying to cut stuff out of here so that make it more straightforward for you. But do know the difference between fine-grained and coarse-grained. And the difference is that fine-grained rocks, you will not see any visible minerals. Now, I think that on the test, you have a picture of a rock, and I ask you to tell me, is it fine-grained or is it coarse-grained? The way that you're going to tell is that coarse-grained will actually have big chunks of visible minerals that will kind of look almost like they're interlocking, and you should be able to see, all of the crystals. So that would be a intrusive, coarse-grained rock. Okay, whereas something that's fine-grained, it's just, you're not going to see any texture to it. It's just going to be, you're not going to be able to see any crystals. Okay, so just FYI, that's how you do that. Now, here's where you need to know the rock names, and you do need to know this. This might just be on the test, like just straight up this table, and probably it'll be labeled like, I don't know, A, B, C or something, and you have to say, what goes to A, what goes to B, what goes to C, etc. So you got to know this table and be very careful, because I could switch things up, and put felsic over here, over there, whatever. So you can't just memorize where things go in this table spatially. You have to know, like, okay, the coarse-grained felsic rock is this. The coarse-grained intermediate rock is this. So the coarse-grained felsic rock is granite. The coarse-grained intermediate rock is diorite. The coarse-grained mafic rock is gabbro. The fine-grained felsic rock is rhyolite. The fine-grained intermediate rock is andesite. And the fine-grained mafic rock is basalt. Okay. Now, you should also know the 3 ways that the mantle can melt. So just really quick, you can raise temperature. So I'm just going to put raise T. You can lower P, lower the pressure. Or you can also lower the melting temperature. And you do that by adding something to it. That's called flux melting. By the way, that's called flux melting. Lowering the pressure to melt the mantle is called decompressional melting. Okay. Now on to sedimentary rocks. You should know the different forms of sediment and the kind of things that can constitute sediment, how each one's created. So there are maybe we could say 4 things that could be sediment, and each of those things corresponds to a different class of sedimentary rock. So the first thing that can constitute sediment is just broken, broken grains of mineral and rock. Okay, and that corresponds to the clastic rocks. You can also have things that are made out of marine shells and tests, and that gives you the biochemical rocks. You can also have things that are precipitated. I'm going to put precipitated minerals that are precipitated out of water, and we call those the chemical rocks. And then you can also have organic matter. I'm going to put OM for organic matter, and that gives you the organic rocks. Those are things like coal. Okay. So I already kind of answered number 39 for you above, just based on the difference between the different classes is what the material that composes the sedimentary rock, the sediment, is made out of. Now number 40. You should know the following sedimentary rocks. Be able to say whether they're clastic, biochemical, chemical, and you should also know their mineralogical makeup. Okay, so let me talk a little bit about this here. I'm going to give myself a little bit more room here to talk. Okay, so first of all, I'm gonna split this up into clastic, biochemical, chemical, and organic. Okay, those are the different classes. Now, the clastic sedimentary rocks, remember that clastic sedimentary rocks are organized by their grain size. So I'm going to start off with the smallest grain size and go to the largest. So the smallest grain size is shale. That's made of clay. Silt stone is made of silt, right? That's the second size. The next is sandstone. And the next is then after sandstone, we get to things like breccia and conglomerate. And those are things that maybe have pebbles or gravel or larger chunks of rock. Okay, those are all made out of broken chunks of rock and mineral, okay, because they're clastic. Biochemical rocks are made of, like I said, shells and tests of microorganisms. They're basically created by life, the material generated by marine life, okay? So for biochemical rocks, we have things like coquina and any of the limestones. If there's any limestone, it's a biochemical rock. Also, chert is under here too. Okay, for chemical rocks, we have gypsum and rock salt. Those are things that are precipitated out of water, just inorganically. That means not by life. They're just precipitates. Inorganic, we have coal. Okay, so those are the ones that you should know for this class. Now, you should also know a little bit about diagenesis. So diagenesis, this is yet again another question that I could ask on the test where you have to maybe write a paragraph to explain. So diagenesis is when you have sediment being converted into sedimentary rocks. That's what we call diagenesis. So diagenesis is anything that takes sediment and turns it into a sedimentary rock. And usually that's that's composed of a few processes. So there are several processes that are involved in that. So first you have dehydration. So that squeezes out the water from the sediment. And then you have compaction. That's where you squeeze out all the extra pore space and air. You compact the sediment together. And then you have cementation. So that's where some kind of natural cement will precipitate along the mineral grains or between the mineral grains. Or perhaps another thing that can happen is something called pressure solution, where you actually have melting and fusion along the grain boundaries just due to high pressure. So those are different processes that are involved in diagenesis. Okay. All right. So what is a metamorphic rock? Okay. A metamorphic rock is one that's been converted from. It's been changed under the solid state. Okay. So maybe we can put a transformed or metamorphosed rock in solid state. And solid state is very important here because once something melts and becomes a liquid or partially a liquid, remember that rocks don't melt at one temperature. They melt over a range of temperatures. So once melting starts, then we start to call that an igneous rock. So everything has to be in the solid state. A protolith for a metamorphic rock is the rock that it starts off as. So you might start off, for example, shale, and shale will transform under pressure and temperature to maybe a slate. That's a metamorphic rock. Okay, so I already answered number 43. So if something melts partially or fully, it's going to be a igneous rock, not a metamorphic rock. Okay, what are the agents of metamorphism? That means what causes metamorphism, and that's heat, temperature, pressure, and also fluids. Fluids can do it too. So especially hydrothermal fluids can alter a rock, make it a metamorphic rock. All right, so in the case of a shale, what happens if you metamorphose a shale? You subject it to high temperatures and pressures. Well, first thing you'll get is a slate, and then with higher temperature and pressure, you're going to get a phyllite. And with higher temperatures and pressures, you're going to get a schist. And then even higher, you'll get a gneiss. And that's the highest grade. Okay, so these are in terms of grade. Okay, you get higher and higher grade. If you start off with a basalt, you're going to get something like, you'll start off with basalt. You'll go to a green schist, then an amphibolite, and with subsequently higher levels of pressure and temperature, you'll finally get to an eclogite. There we go, like that. Sandstone will transform into quartzite, and a limestone will transform into marble. Okay, so I especially want you to know on the test these kind of like the protoliths and how the protoliths, which metamorphic rocks they transform into, because as we go through this class, I'm going to talk about like, oh, there are marbles here, there's quartzite here, there's green schist here, and you should know kind of intuitively, oh, that means that there's a green schist, that means that's just a metamorphosed basalt, or that's quartzite, that's just a metamorphosed sandstone. Okay, so I want you to especially know the protoliths and what they change into. Okay. All right, so what are some changes that take place during metamorphism? So there's a lot of different things that happen. You can get neocrystallization. That's when new minerals form. Things like, for example, there are crystals, kinds of minerals that are just solely metamorphic minerals, like kyanite or andalusite or sillimanite, garnet, things like that. You can get recrystallization. Recrystallization is when small crystals will recrystallize into larger crystals. Okay, so they reform and reorganize and turn into larger crystals. That's a very common process. It happens especially with quartzite and limestones. Another thing that happens is something called where you get we can call pressure solution. And pressure solution happens when you get elongated grains, squeezed grains like this. And that's because the things that were formerly round get squeezed by the pressure, and they'll kind of collapse like this and align themselves to the different to the direction of the stress. Okay, so if they're getting squeezed like that, almost like if you imagine squeezing something in a vise, it's going to get smushed, and that happens as well. Another term for that is foliation, and that's when the grains will orient themselves according to the main direction of stress. Okay, so then the next thing here is plate tectonics. So this is another question that I often put as, I'm going to give myself a little bit more room here. It's something I often put as a kind of short answer question. So you should be prepared to answer this with a paragraph. So what are some of the lines of evidence that Alfred Wegener proposed to support his theory of continental drift? So the 4 lines of evidence that he provided, I'm going to write this all down here, is the first one, the kind of most intuitive one, is matching of coastlines. So that means that, and by the way, when you do this on the test, don't just answer 4 words, like 4 bullet points. That's not going to be good enough. I'm only going to give you maybe half credit for that. I want you to explain each of these, just like with 1 sentence. It doesn't have to be amazing. Just maybe like a 1-sentence explanation of each of these, so that I can see that you understand. I don't want you to just memorize a word. I want to see that you can understand a little bit the science behind, or the evidence behind this. Okay, so matching coastlines. So that just means that the coastlines of the different continents can fit together almost like a puzzle. Okay. There's also from geologic evidence and mountain belts. And what this means is that mountain belts and also specific geologic rock units match together if you put all the continents back together the way that they seem to fit. So that means that you find the same exact rock units on like South America as you do as Africa. That's because you can see South America and Africa fit together perfectly, nice and snug. And you also find the same exact rocks on either side of the coast. Okay, so that's what we mean by matching geology, matching mountain types, things like that. All right, next part is for fossils. Okay, so again, same kind of thing. You find the same fossils on South America as you do on Africa, the same animals, and that seems a little bit weird because some of them have very restricted ranges on those continents. Some of them are plants, and plants obviously aren't going to get up and move from one side of the Atlantic to the other. Some of these things are also, I know that sometimes seeds can travel very far, but a lot of these plants are ferns, and ferns don't even make seeds. They make spores, right? They're called sporophytes. So it's hard for those spores to travel all across the Atlantic Ocean, as you can imagine. So there's a lot of different evidence from fossils. You can go back to the lecture and listen to more if you want more details. And the last is from glaciers. So, when glaciers move across the landscape, they will scrape and leave scratches and striations that show the direction of movement. And again, if you put all of the continents together, you find that these directional indicators left by glaciers all match up. So let's say this is South America and this is Africa, right? And then you'll find that these directional indicators match up if you were to put South America and Africa back together, if that makes sense. Okay. So anyway, we already talked about differences between the asthenosphere and lithosphere. So just make sure you know that because it's important for plate tectonics as well. You should know the 3 kinds of plate tectonic boundaries. So there's convergent, that's where the plates are coming together at a boundary. There's divergent, that's where they're diverging, they're moving apart along the boundary. And there's transform, that's when you have a boundary like this, and one is sliding this way and one is sliding that way. Okay, so that's how that works. Now, for convergent boundaries, you should know the difference between continental convergence and ocean continental convergence. Okay, so when 2 continents come together and converge, I'm going to draw 2 continents. Okay, converging. They're going to build up mountains and thrust fold belts, but they're especially going to build up mountains as they collide together. So this is like the Himalayas. Okay. Now, when you have the ocean crust, which is much thinner and denser, collide with a continent, it's going to subduct, right? It's going to go underneath the continent. And there it's going to melt, and it's going to melt due to flux melting. You know, the melting temperature is going to change because of the water that gets injected into the mantle. And then that's going to create volcanism here, and you're going to get andesitic volcanoes that erupt here. Okay, so that's a subduction zone. You should also be able to label a diagram of a subduction zone. Again, I'm going to give myself some room so I can do this for you. Now, you're not going to have to do this, of course, on the actual assignment. Like, you're not going to actually have to do this on your assignment, on your test. But you will maybe have to, like, you know, label it. Maybe that's or getting frustrated how I'm supposed to say, but you might have something that's labeled already, you know, like A, B, C, D, and you have to identify which each feature is. Okay, so this is what a subduction zone looks like. Okay, you have the ocean crust, and it's subducting beneath the continental crust. Okay, I'm going to put CC for continental crust. Now, there's mantle below the crust, right? And there's mantle lithosphere, and then at a certain point there's mantle asthenosphere. Okay. Now, there's also a very deep part of the ocean here called the trench. And there's flux melting going on here. That's what happens when the water from the ocean crust subducts, and it lowers the melting temperature of the mantle, and it creates volcanism. Okay, and then you get andesitic volcanoes here. They're called arc volcanoes. Okay, those are called arc volcanoes. So you should be able to, you know, label all of that stuff. Now you should be able to give a. Now this is another question where I ask you to write something. Okay, so you should be prepared to write again a paragraph about why we get volcanism at a subduction zone. So I'm going to say this all really slowly. By the way, there's also a video that I'm going to link you to. Maybe I can link you to it in the comments, but you can watch that video, and that explains this process in great detail. So anyway, if you go to the divergent, why we have volcanism in a divergent plate geometry and why we get it at a subduction zone. So let's do subduction zones first. The reason that you get volcanism at a subduction zone is, again, going to this picture above. What happens is that there's water in the ocean crust, right? It's soaked in deep into the ocean crust. So that water is eventually exuded, and it lowers the melting temperature. Okay? It lowers the melting temperature. A lot of people mess this up and they say, oh, the water's really hot and it melts the rock. No. The water is not hot at all. If anything, the water is much cooler than the surrounding rocks. What the water does, the role of the water is that it lowers the melting temperature of the mantle. So it causes the mantle to melt without changing the temperature, without changing the pressure. It just lowers the melting temperature, and that causes melting. Okay, so that's called flux melting. Now, at a divergent boundary, you get something opposite. Okay, you get this situation where you're diverging. The mantle asthenosphere is welling up. Okay, it's welling up and it's rising. And as it rises, it goes from an area of high pressure to an area of low pressure. And as it decompresses from a high pressure to a low pressure, it melts due to lowering the pressure. And remember, that is one of the three ways to melt the mantle, is you just lower the pressure. Okay, so that causes melting as well. All right, so you should know also various lines of evidence that support plate tectonics. I already talked about that. I talked about Alfred Wegener's things that support the theory of continental drift, but you should maybe, what I'm referring to here is probably referring to the evidence that emerged after Alfred Wegener's death that talks about his, sorry, somebody's talking outside, I'm getting distracted. You should know the various lines of evidence that support plate tectonic theory. So those are things like magnetic anomalies, And number 2 is echo sounding. And number 3 is also, what am I trying to say? Radiometric dating. So I don't want to go through all these and explain them in great detail because it's really, especially like magnetic anomalies, it's a real mouthful. But I would just say if you want more details on these, you should have some familiarity with them. I don't ask you to describe these like in a paragraph. Like there's no short answer questions about these. But you might have to answer some kind of specific multiple choice questions about magnetic anomalies. So make sure that you do understand magnetic anomalies, at least basically. You don't have to have a great in-depth understanding, but you should have a little bit of understanding about magnetic reversals. Okay. And things like that. So go back to the lecture and, again, listen to that point in the lecture about magnetic anomalies, echo sounding, radiometric dating. Just make sure that you could explain each with about a sentence or 2 sentences, okay? That's the kind of expertise you need to have about it, okay? I already talked about this. Just know that, of course, the core, the outer core is the only one that's liquid, okay, of all the different shells that we talk about. Okay, now also, is there convection in the mantle? So hopefully you know by this that this is yes. Okay, so the mantle is convecting, right? There's convection in there, and that's what creates the plate tectonics, okay? So that's a very, very important point. We definitely want to make sure that you understand that. And just know that the plate tectonics, the movement of the continents, it's all driven ultimately by mantle convection. Just mantle convection. And mantle convection, in turn, is just happening because Earth is trying to lose its heat. That's all there is to it. It's just kind of Earth's way of cooling off, is plate tectonics. Kind of sounds like a funny thing, but it's true. All right, so on to geologic time. You should know the 3 types of unconformities and be able to recognize them. So you could very well, on the test, have some pictures, and you're going to it's going to show you unconformities, and I'm going to ask you, what kind of unconformity it is. So the easiest one to recognize is an angular unconformity, and that's where the layers on the bottom are at a different angle to the layers on top. Okay, so the unconformity would be right there. By the way, I should also mention, what is an unconformity? Well, it's just a missing time in the rock record. Okay, it's where you're missing some time out of the rock record. So there was an interruption to deposition. Okay? So that would make an unconformity. There's an angular unconformity. Another thing is when you have a crystalline rock, like let's say granite, and then on top of that you have maybe some layers of sedimentary rock on top of the granite. Okay, well, you know that there was not deposition at the granite because granite's it's not a sedimentary rock, so it couldn't be deposited. So you know that there must have been an interruption to deposition if you see the granite like that. Or it could be a metamorphic rock too. It just has to be either a metamorphic rock or like a plutonic rock is usually what you're talking about. Okay, so that's called a nonconformity. And this is an angular unconformity. And then the last kind is really hard to see because you could have deposition, and then something happens and deposition just stops. And there's an unconformity. But then deposition starts again. And you would really have no idea. And sometimes this can be really hard to see, but that's called a disconformity. And the reason, or the way that you can tell a disconformity is because the layers on top and on the bottom, above and below the unconformity, are both sedimentary rocks, but they're all at the same angle. So the beds are all in the same position. So it's really hard to pick up on that, okay? All right, now you will have something on the test like this. Okay, it's not going to be this one exactly. It's going to be different, but I'm going to ask you specific. Basically, what I'm going to do is I'm going to ask you to put the events in order. Okay, so for example, this one. The first event to occur would be, okay, so there's a few events. There's deposition of B, deposition of O, deposition of X, deposition of D, deposition of A. Those are all sedimentary rocks. There's the intrusion of M, that's a granite layer, and there's a fault. Okay, so I'm going to ask you to put all those events in order. So the first event to occur was B. Okay, so B got laid down. We know that by superposition, right? Because it's at the bottom. Now I noticed on the homework, a lot of people thought to themselves, "Oh, but look, M is even lower than B. It's maybe not even lower, but it's at the same depth at B. So I'm going to put M as number one." And that was incorrect. I marked people off for that on the homeworks, on the lecture assignments, because yeah, M is at the bottom, and you might think by superposition it's the bottom, it's the first thing to happen, but you notice that M is actually a granite intrusion that is cross-cutting a lot of things like D and A and blah blah blah. So remember that according to cross-cutting relationships, A and D and X and O and everything else that gets cut by M had to be there first. Okay, so that means M had to come after those things. All right, so the next thing that happened according to superposition is O. Okay, so O right there, and O is on top of B. X is on top of O, and then D is on top of that, and A is on top of D. And we know that after that comes M. And we know that because M cuts A. M cuts A. You can see that right there and right there. And we know that after that came fault J, because you can see that the fault right here cuts M. You see that? So we know that fault J came after M. All right? So that's how that works. And you should be able to do that on the test. You're going to have a question like that, so be prepared. All right, for radiometric dating, I'm not going to have you memorize every single kind of isotope and every single parent and every single daughter. You don't need to do that, but I would like you to know, make sure that when you come to the test, you know at least one pair. So there's a lot of things that you could talk about. You could talk about carbon-14 going to nitrogen-14. That gives us the radiocarbon dating. Now, we don't actually use that very often in geology, but it is something. You could talk about potassium-40 going to argon-40. You could talk about any of the uranium series ones, like uranium-208, right? Or sorry, uranium-208. Uranium-230, 235, or uranium-238, and how they go to either lead-207 or 206 or 208, right? You could also talk about thorium, the thorium-232, going to lead. I think it goes to lead-207 if I'm not mistaken. Can't remember exactly now. But I won't take credit off. You get the lead-206 or 207 confused, because I can't even remember off the top of my head right now. But you should know one of those things. Also, you should know, for example, rubidium, 87 going to strontium 87, like that. Okay, so there's some examples for you. You should know what an isotope is. Isotope is just an atom that has, of a particular element that has more or less neutrons, and so it has a different mass number. So it has the same atomic number. Atomic number is just the number of protons. That's, determines what element it is. So same atomic number, different mass number. Okay, is radiocarbon dating useful, generally speaking, for dating rocks? And the answer to that is no, it's not. Because, for one thing, many rocks don't have carbon. It's not really a very common element in the earth and in the crust. Also, another thing is that the half-life for carbon-14 going to nitrogen-14 is very, very small. It's only 5,700 years. And that might seem like a lot to you, and I guess it is a lot in human terms, but for geologic materials, it's very short, right? Usually we're talking about things that are millions of years old, so that there might be 1,000 half-lives, and after 1,000 half-lives, there's basically no carbon-14 left. So it has too short of a half-life. That's the problem with radiocarbon dating. So what kind of rocks can be dated with radiometric techniques? Okay. And you should explain with all the nuances. By the way, nuances are kind of like the little details, the little kind of complicating details, in case you're not familiar with that vocab word, nuance. But anyway, what kind of rocks can be dated with the radiometric techniques? Generally speaking, the best rocks to do are volcanic. Second best are plutonic, igneous rocks. Okay, but igneous rocks are the best. Okay, sedimentary rocks, it can work only. So generally speaking, sedimentary rocks, no, but it can work if you have the mineral glauconite. Glauconite is a sedimentary mineral. It's a mineral that's common in sedimentary rocks, some sedimentary rocks, and it can be radiometrically dated. What about metamorphic rocks? Generally, not great, but it can work, but it usually gives a date for the metamorphic event, not the actual age of the rock per se, because remember that metamorphic rocks start with a protolith. So when you date a metamorphic rock, if it is giving a good date, you're getting a date for the metamorphic event, not the protolith formation. So you're not really getting like the true age of the rock. Okay, so the atomic number of nitrogen is 7. How many neutrons does nitrogen-14 atom have? So when you see something like nitrogen-14 or carbon-14 or uranium-230, 235 or 238, that number right there is the mass number. And mass number equals the protons plus the neutrons. Okay? Protons plus the neutrons. So if I tell you the atomic number of nitrogen is 7, that means that the number of protons, the atomic number, is 7. So if I know that P equals 7 and P plus N, protons plus neutrons, equals 14, then you can figure out how many neutrons there are. So in this case, it would be 7, right? Because 7 plus N equals 14. You subtract 7 from both sides. That equals 0, and then you get N equals 7. Okay, so it's a little bit of algebra. Hopefully it's manageable. Okay, now you will have to calculate the age of a rock given a certain number of half-lives that have occurred and given a half-life. Okay, so for example, the half-life of uranium-235 is 0.7 billion years old. So after 0.7 billion years, half of uranium-235 will decay. So if an igneous rock initially has 100 atoms of uranium-235, and then over time 50% of those atoms decay, how old is the rock in billions of years? Well, if 50% of those atoms have decayed, that means that one half-life has passed. So it's really just asking if one half-life has passed, how old is the rock? Well, it's just one half-life, and one half-life is 0.7 billion years. So that is a question that doesn't really require any math, but it's really just kind of testing you to make sure that you understand what a half-life is, if that makes sense. So hopefully that made sense to you. So it doesn't actually contain any math in it. It's just kind of logic, if anything. All right, so final thing here, and then we're going to knock off. We only have a few questions left. Evolution and diversity of life. So one thing is that you need to be familiar with, I ask a lot about kind of diversity and how we split up, giving myself more room here, life. So for plants, I ask about the different subphyla of plants. Phyla of plants, I should say. So plants is a kingdom, and we have four subdivisions of that kingdom, the 4 different phyla. So those are what are called the non-vascular plants. Those are called bryophytes. Those are things like mosses. There's other things too, like liverworts and hornworts that are non-vascular plants. Okay, so those are things that don't have a vascular system. Then there's the sporophytes. Those are things that have a vascular system, but they don't have seeds. So these are things like ferns. Okay. Then there are things that have seeds and have vascular systems, but they don't have flowers and fruits. Those are the gymnosperms. And then finally, there are things that have flowers, fruits, seeds, vascular systems, and all of the above. And those are called the angiosperms. Okay. Now, you should know the 6 kingdoms of life and kind of know a little bit about the essential characteristics of each kingdom. So kind of like what makes that kingdom unique. So first ones are the archaea and bacteria. I will not ask you the difference between archaea and bacteria because it is something I don't even understand, because it's something that is it's something only a microbiologist would really understand. I've tried to understand the difference, and it's, like I said, it's a very expert topic that I would never ask you about. But there's archaea and bacteria. There are substantial differences between them, but something that you would really have to have a lot of microbiologic knowledge about. So, but these are prokaryotes. Okay, that means that they lack a nucleus in their cells. And they're single-celled organisms. Then there are the protists. Those are eukaryotic. And they're often single-celled. Okay. Next are the plants. Plants are eukaryotic, but now they're multicellular. Okay. And they often are, of course, photosynthetic. Then there are the animals, and there's the fungus. And these animals are, of course, multicellular, they're eukaryotic, and they're also capable of moving around on their own, which is different, of course, than plants. That's kind of one of the distinction between plants are photosynthetic, and they're incapable of their own powered motion, whereas animals are, of course, can move around, and they're animated, right? That's what gives you the word animal, okay? They're animated. And fungus is, of course, eukaryotic. It's multicellular. They're often, though, not photosynthetic. They're actually parasitic in most cases, or they're breaking down. They're not parasitic, I shouldn't say. Excuse me. They're breaking down decomposers and breaking down decomposing material. Okay. So what's allopatric speciation? So there are a lot of different ways that species change over time and create a new species. So a speciation is just an event that creates a new species. There are a lot of different things that do that. I don't ask you for everything. I just want you to know allopatric because it's just one maybe common example of how new species are created. So again, you should be able to explain that with a couple sentences. That could be a short answer question. And in short, I'll just give you a brief explanation. Allopatric speciation occurs when you have a single population of a species and then something happens that changes their habitat and the population is split and there's no more I can say contact between the two populations of that species. Well, over time, those two populations start to diverge, especially if their habitats have become very different. They're going to start adapting to their specializing and adapting to their new habitat, and it's going to eventually create to enough change and divergence that the two are no longer going to be able to mate, and there'll be now a new species. Because remember, what makes a new species, what defines a species, is you're no longer able to mate and reproduce with members outside of your species. Okay, so that's literally what makes a new species, right? So once there's no more mating happening between the two species, we consider that a new species. Okay. So please explain the difference between the evolutionary theories of phyletic gradualism, punctuated equilibrium. Now, again, this will very well be a short answer question on there. This is something I really wanted you to do in the reading, but if you didn't do it in the reading, I will give you a short explanation right now. Phyletic gradualism states that species come into existence by slow, steady changes. And there's going to be a very slow, gradual process of the phyla changing and creating a new species. Okay, punctuated equilibrium is different. It states that actually species and populations are stable for a very, very, very long time, maybe 10 million years, but then something will suddenly happen that punctuates their period of equilibrium, and they're going to create a new species very fast, actually. They think that speciation is something that happens very fast. The reason that punctuated equilibrium is generally favored over phyletic gradualism among biologists is that in the rock record, fossil record, we don't really see very many good examples of slow changes happening in species. Normally what we see is a new species suddenly appearing with very few transitional fossils in between. Is that a result of just poor recording in the fossil record, just poor preservation? We don't really know, because it's just not. It's just something that's difficult to determine, because it's something that we have so little information about what happened in history. All right, so you should also know the difference in the phyla of the animal kingdom, and you should be able to classify various animals into their proper phylum. So you should know the different phyla. There are 10 phyla for animals. Okay, the first one, so I'm going to write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and you should know a little bit about how to start classifying animals. This is going to become very important as we start moving through geologic history and life history. Okay, so you have to know these things. Some of these are more important than others. So the first one, the simplest animal is porifera. Porifera are sponges. So they're marine sponges, and I think you've heard of those things before. Okay, so it's a filter-feeding marine animal, sessile, living on the bottom of the seafloor, and it filter feeds. Okay. Next are the cnidaria. These are things like corals, sea anemones. Oh man, how do you spell anemone? Sorry, I don't know how to spell sea anemone. Coral, sea anemone, also jellyfish. Okay. The next are the there's some that you don't really need to know as much, like platyhematants. And the reason that you don't really need to know those is because you maybe know that they exist. These are things like flatworms. They're not very important for us, though, because they're rarely preserved in the rock record. Okay, there's also nematoda, which are roundworms. And again, same thing as flatworms, platyhematants. They're important evolutionarily speaking, but we just don't see them in the rock record because they don't have hard parts and they're not preserved. So the next one that you should know are the not cephalopods. Oh, I'm losing my mind. Oh, mollusks. Sorry, mollusca. And those are things. We actually break those up into a few important groups. There's gastropods. Those are things like snails. There are cephalopods. Those are things like, and by the way, snails could be land snails or sea snails, by the way. Cephalopods are things like squid and octopus. When we start studying things like ammonites are also cephalopods. Okay. Then we have arthropods. Those are things like insects. And, arachnids and crabs, crustaceans, very important group. Okay. We also have echinoderms. Those are things with five-fold symmetry. So those are things like sea stars and sea lilies and sea stars. and brittle stars, things like that. They have fivefold. Also, sea cucumbers. Those are echinoderms. When we get to this, we crinoids as well are types of echinoderms. Okay. Next are chordates. And that's what you are, right? You're a chordate. Okay. And what am I missing? I only have 8 here, so I'm wondering what I'm missing. I'm going to have to go back and remind myself. There might be something. Gosh, what is it? Or maybe there's not 10. Maybe there's fewer than that. Okay, I'm a little bit... Sorry, I have to cheat and go back. There's something I'm missing. I don't know what. Okay, sorry. Looking up the lecture because there's something I'm forgetting, and I'm trying to remember what it could be. So here's the lecture. Sorry, I just totally forgot. No, it's not that. Platyhematins, mollusks. Oh, yeah, Annelida. I forgot about Annelida. Annelida should actually go right here. Yeah, Annelida are things like segmented worms, so like leeches and earthworms. Again, they're not as important in the rock record because again they're mostly soft-bodied, so they're often not preserved. So I got sponges, cnidaria, flatworms, roundworms. Rotifers are types of... Oh, I forgot. Yeah, I never talk about rotifers because the rotifers are a type of very small planktonic life, zooplankton, but they're not really important in the rock record. Mollusks, annelids, arthropods are kind of... Okay, so I got everything, yeah. So there were these groups that we don't really talk about too much in this class, but you should definitely know the ones. You can kind of forget about platyhematites and nematoda and rotifers. They're not really very important for fossil life. Annelids are kind of come up rarely a little bit, but these are the ones I have written here, these 8 that you should really know. So, or actually, they're not even 8. What? Porifera, cnidaria, annelida, mollusca, arthropoda, echinodermata, and chordates. Okay, so those are the ones I really want you to know. All right, so that's it. I've been going on for a very long time, hour and 20 minutes. So I'm going to let you go, and good luck studying for this test, and please let me know if you need any more help or any more guidance. Okay, and I will talk to you later.